Okay, so we're going to finish off this chapter today. You guys are going to have a quiz on chapter 8 tomorrow. And then we'll be doing review. Most of you, I think, already got your review assignment. So on Wednesday, we'll go through the chapter 7 and chapter 8 quizzes. And then Thursday will be your test on this next unit. So we should get through chapter 9 and part of chapter 10 before Christmas, for sure. And then we'll just have chapter 11 to finish off after Christmas. And then it'll be getting ready for the diploma exam. All right? So, looking at some applications of logarithms. Here's another example of using logarithms in an equation. Paleontologists can estimate the size of a dinosaur from incomplete skeletal remains. For a carnivorous dinosaur, the relationship between the length S in meters of the skull, and the body mass, m in kilograms, can be expressed using that logarithmic equation, where S, remember, is the length of the skull, m is the body mass. Determine the body mass to the nearest kilogram of an Albertosaurus with a skull length of 0.78 meters. So we're using that formula. 3.6022 log S equals log M minus 3.4444. S is the length of the skull, M is the mass, and we want to determine the body mass M to the nearest kilogram of that dinosaur with a skull length of 0.78 meters. So S will be 0.78. So these logs are common logs, and we can figure out what the left side of the equation works out to by going 3.6022 times the log of 0.78. So that's negative 0.39 if we round it to write it down, equaling log m take away 3.4444, which we will add that value to both sides. And that'll give us log of m by itself. That's 3.06 if we round it to write it down. And then to find out what m is, remembering that this is a common log base 10, we'll convert from logarithmic to exponential. We'll start with the base and cycle through. So it'll be 10 to the power 3.06 equals m. And again, we wrote down that 3.06 as a rounded value. It's always best to use the entire number in the calculator. So we'll go 10 to the power of the previous answer. That uses that whole decimal. And so to the nearest kilogram, it'll be 1,137 kilograms. And let's just see if it would make a difference if we just did 10 to the power of 3.06. Would it make a difference in the answer? And it absolutely would. It absolutely would. So using the entire decimal is important. Okay? And there's a question on the next page that is, I mean, very similar. Only in this case, they give us the body mass and we want to find the length of the skull. So let's go on to this next one here. When an animal dies, the amount of radioactive carbon-14 in its bone decreases. Archaeologists use this fact to determine the age of a fossil based on the amount of carbon-14 remaining. The half-life of carbon-14 is 5,730 years. So that means it takes 5,730 years for the amount of carbon-14 to decay to half of what it started with. That's what half-life means. How long it takes for it to decay to half of what it started with. So head smashed in buffalo jump in southwestern Alberta is recognized as the best example of a buffalo jump in North America. So what the First Nation people used to do is they used to chase the buffalo towards this cliff. And the buffalo would run off the cliff and it was far down and they would die when they hit the ground. And that saved them trying to catch them and shoot them with their whatever they were using. They actually chased them and ran them off the cliff and they died when they hit the ground at the bottom. And you can go there. It's south of Black Diamond, south of there's another town that's a little bit bigger, but it's south of Calgary. Okay, and you can go there. It's a historical site. So the oldest bones unearthed at the site had 49.5% of carbon-14 left. How old were the bones when they were found? So again, we're not given any equation here. We need to come up with our equation. But remember, we are given on the formula sheet that exponential formula A equals A times B to the power T over P. So that is the formula that is on the formula sheet, where A is the initial amount, B is the growth factor, T is the time, and P is the growth period. In this case, P would be 5,730 years. That's how long it takes for the amount of carbon-14 to decay to half of what it was. Okay? So again, A is the initial amount. And in this case here, we're not told what it is, so I'm going to let it be represented by A sub 0. B is the growth factor, which in this case would be a half, because the amount of carbon-14 is being cut in half every 5,730 years. T is the time, which would be in years, because the growth rate is in years as well, or the growth period. And that is 5,730 years. And I should have written there, this is the growth period. How long it takes in this case for the amount of carbon-14 to be cut in half. Now, the oldest bones unearthed at the site had 49.5% of the carbon-14 left that it initially had. So that means the amount at the end in this case will be 0.495 times the amount started with, which is A sub 0. So this is the left side of this equation. The left side is A, the amount remaining. And in this case here, we're told that the amount remaining is 0.495, 49.5% of what they started with. So that's the left side of the equation. The right side has little a, which is A sub 0, the initial amount, times the growth factor, which is a half, to the power T over 5,730. So there's that equation set up. We can divide both sides by the A sub 0 to eliminate them. And so we are now left with 0.495 equals 1/2 to the power t over 5,730. So we need to solve this exponential equation. When we first looked at solving exponential equations back in chapter 7, we made the bases the same, and then the exponents were equal. Can't do that here though. But remember, this is one of the uses of logarithms. You can solve any exponential equation using logarithms by converting from exponential to logarithmic, by starting with the base and cycling through. Remember that the bases are the same no matter what form you are in. This exponential function has a base of 1/2, so when you write it as a logarithm, it'll be log base 1/2 of 0.495 equals t over 5,730. And you can use your calculator to find out what the left side is. If you have the log function in your calculator, this newer operating system, you can do that. If you don't, you use the change of base identity. Do the log of 0.495 divided by the log of 1/2. So the left side works out to be 1.014, and that's rounded, but I'm keeping the number in my calculator for the next step, which is multiply both sides by 5,730. You see, the amount of carbon-14 is cut in half every 5,730 years. So if there's 49.5% left, that means it would have been decaying for a little bit more than 5,730 years. Because after 5,730 years, there'd be exactly 50% left. There's a little bit less than that left now. So our answer is going to be slightly more than 5,730, which we will get here if we multiply both sides by 5,730. And so it's actually 5,813 years old. So it doesn't ask us to round it to, so let's round it to the nearest year, approximately 5813 years old. Right, so in this case, again, we have to come up with the formula. And the one on the next page, in this case, we're given the formula, but we should be able to look at it and see where everything comes from. The rate at which an organism duplicates is called its doubling period. The general equation n at t equals n sub 0 times 2 to the t over d, where n is the number present after time t, n sub 0 is the original number, d is the doubling period. We call that the growth period. In this case, we're saying doubling period because that's how long it takes for the number of organisms to double. E. coli is a rod-shaped bacterium commonly found in the intestinal tract of warm-blooded animals. Some strains of E. coli can cause serious food poisoning in humans. Suppose a biologist originally estimates the number of E. coli bacteria in a culture to be 1,000. After 90 minutes, the estimated count was 19,500. What is the doubling period of the bacteria to the nearest minute? So we're using this formula. N at t equals n sub 0 times 2 to the power t over d. So the reason the base is 2 is because the number of organisms is doubling every so often, and we're trying to find out what is that doubling period. N at t represents the number at the end, which was 19,500, and that equals n sub 0, the initial amount, which we're estimated to be 1,000, times 2 to the power t over d. T is the time, which is 90 minutes. We want to know what d, the doubling period, is to the nearest minute. So we need to solve this equation for d. We can start by dividing both sides by 1,000. So the 1,000s cancel on the right, and on the left, dividing by 1,000 moves the decimal 3 spots over. So you'll get 19.5 equals 2 to the 90 over d. So once again, we have an exponential equation that we need to solve. Can't make the bases the same. Can't express 19.5 with the base of 2. So we use logarithms. We convert from exponential to logarithmic. We start with the base and cycle through. So it'll be log base 2 of 19.5 equals 90 over d. Before we touch our calculator, let's get d by itself. By multiplying both sides by d, we'll get d times log base 2 of 19.5 equals 90. And then d will equal 90 divided by log base 2 of 19.5. So 90 divided by log base 2 of 19.5. So approximately 21 minutes. That's how long it takes the number of E. coli bacteria to double. So let's go ahead and look at some questions involving compound interest. It's different than simple interest, because simple interest, the interest is just calculated once at the end, where with compound interest, the interest is calculated at regular intervals, and the interest is added to the principal. Right? So compound interest is standard in finance and economics. Simple interest more frequently, used more infrequently, I should say, although certain financial products may contain elements of simple interest. The effects of compounding depends on the frequency with which interest is compounded, as well as the periodic interest rate which is applied. In order to define accurately the amount to be paid under a legal contract with interest, the frequency of compounding, whether it's yearly, half-yearly, quarterly, monthly, daily, etc., and the interest rate must be specified. And so this table just shows the effects of how often the interest is compounded or calculated. The more frequently it's calculated, the quicker it grows, is basically what this chart shows. It shows the amount of an investment that started at $1,000. Now, we're not told what the interest rate is, but the interest rate is the same for all of these graphs, from yearly to quarterly to monthly to continuously, which would be probably daily. Okay? But this shows how the money is growing, and it grows the most when the interest is calculated more frequently. So some of the common compounding periods that we're going to be seeing is annually, which is once a year, semi-annually, which is twice a year, quarterly, which is 4 times a year, monthly is 12 times a year, weekly is 52, and daily would be 365 times a year. Now, there is a compound interest formula. You may have seen that before, but that's not given to us on the formula sheet. What's given to us on the formula sheet is that exponential growth decay formula, y equals a times b to the power t over p. That's what's given to us. Right? But it's the same formula that we just used, so the parameters, the variables, will represent the same amount, or the same things. A is the initial amount, B is the growth factor, T is the time, P is the growth period. And then you always have to make sure that the time and the growth period are in the same units, whether they're both in years or both in months or whatever the case is. They just have to be in the same units. So again, this is the formula that we're going to use. Little a is the initial amount. B is the growth factor. If something is increasing in value, the growth factor is greater than 1. If it's decreasing in value, if it's decaying, then the growth factor is between 0 and 1. T is our time, and P is the growth period. How long does it take for that growing to take place? So we'll do all our questions using this formula because this is the one that's given to us on the formula sheet. So this first example, $5,000 is invested in a 7-year GIC. So that's just a guaranteed investment certificate. You can buy them from the bank. So you give them your money and you sign the deal, and they're going to keep that for 7 years. And at the end of the 7 years, they guarantee this is what they're going to pay you in interest. Okay? If you have to take it out early, then the deal's off and you get your money back, but no interest. If you want to get the interest, you got to leave it in there for, in this case, the full 7 years. So this 7-year GIC is compounded quarterly at a rate of 3.5% per annum, which is per year. Determine the value of the investment at the end of the term, and then also how much interest was earned. So we're going to use that same formula. Y equals A times B to the power T over P. A is the initial amount, which would be 5,000. We have to do some work here, though, to figure out what B is, and here's the reason why. The interest rate is given as an annual rate, 3.5% per year, but it's being compounded quarterly, which is 4 times a year. So because of that, B has to be calculated by taking the rate, annual rate, and dividing by 4, because quarterly is 4 times a year, or every 3 months, but it's 4 times a year. So to find B, we'd have to take the annual rate, 3.5%. And it doesn't matter whether you convert it to a decimal first or after, but you have to convert the percent to a decimal at some point. So I've converted it to a decimal first, and then I'll divide that by 4. So 0.035 divided by 4, there's the quarterly interest rate. This is what they would use every quarter to calculate your interest. 0.00875. So 0.00875. The annual rate divided by 4 because it's being compounded quarterly. Now T is 7 years, and P, which again is the growth period, and this is happening every 3 months. Okay? Now remember, we said that in order to do this, T and P have to be in the same unit. Right now, they're not. Right now, they're not. But if we go 7 times 12, 7 years, and convert that into months, there's 12 months in a year, I think that's 84 months. Yeah. Okay, so Y, which in this case would stand for the final amount. So let's use A, capital A for the final amount, equals 5,000 times. Now, I said that B was 0.00875. what I forgot to mention is that we'd have to add a 1 to that. And here's the reason why. Every quarter, every 3 months, interest is calculated. You're going to have 100% of what you had before plus 0.00875 more. So you need to have that 1 there. Your money is growing. So you're going to have 100% of what you had plus 0.00875 more. So the value of B then is 1.00875. And that's raised to the power 84 divided by 3. So 84 divided by 3, is that 28? Yep. And here's a quick check to make sure you have the right exponent there. Here's a quick check to make sure you have the right exponent there. How many times will the interest be calculated? Well, it's compounded quarterly, which is 4 times a year for 7 years. 4 times 7 is 28. The interest is going to be calculated 28 times. So you could have used that to get that exponent. Instead of worrying about T and P, what are they, making sure they're in the same units, you could have got the exponent by just using some logic. It's compounded quarterly, which is 4 times a year for 7 years. The interest will be calculated 28 times. And that's what we got when we divided RT by P. So now we can just go to our calculator and punch this in. 5,000 times 1.00875 to the power 28. So at the end of the 7 years, that $5,000 investment will be worth $6,381.30. That's what it's worth. And the interest will be the difference between what we started with and what we ended up with. $1,381.30 is the interest. Okay? Example 2, Kelly invested $2,500 for 4 years, compounded semi-annual, and received $843.26 in interest. What is the annual interest rate? So the amount at the end will be A, the initial amount, times B, the growth factor, to the power T over P. A stands for the amount at the end, which will be the principal plus the interest. Right? Her initial amount was $2,500. She received $843.26 in interest. So if you add those two together, that's how much she had in her account at the end of the 4 years, which will be $3343.26. Again, adding the $2,500 and the interest $843.26 together equals little a, which is the initial amount of $2,500. Now, we've got to do some work to get, actually we don't, because we're trying to find out what the annual interest rate is. So in this case, we need to find out what B is to the power T over P. Well, T is the time, which would be in years. In this case, it's compounded semi-annually, which would be every 6 months or every half year. So if we change the 4 years to months, 4 times 12 is 48, divided by 6 months, which is how often the interest is calculated. 48 divided by 6 is 8. Which is how many times the interest would be calculated. It's being compounded for 4 years, twice a year. Twice a year for 4 years, you're going to have 8 different times the interest is calculated. So again, in this case here, we're going to have to figure out what B is. Remembering that B is actually broken down to two parts, 1 plus I, where I would be the semi-annual interest rate. Okay? So let's solve for B first, and then we'll go back to that. You can divide both sides by 2,500. And that at least gets the exponential part by itself. So we'll have B to the 8th equaling 3343.26 divided by 2,500. 1.337, just to round it, I'll write that down. There's more decimals there, but we got them in our calculator. And now to find out what B is, we would take the 8th root of both sides to get rid of the power 8 on the B. We'll take the 8th root of both sides. And so back to the calculator, the 8th root of that, 8th root of the previous answer is 1.037. That's what B is. But remember, B is broken down into two parts. Because the money is growing, it's 1 plus I, where I would be the semi-annual interest rate. B actually equals, let's write it here, 1 plus I, where I equals the semi-annual rate. So 1.037 is equal to 1 plus I. Okay, I'm looking at this right here. To get I by itself, you would subtract the 1 from both sides, which would leave you with 0.037. So that is 3.7% every 6 months. The question wants to know what the annual interest rate, though, is. So you'd multiply that by 2. So it'll be 7.4% per annum. There's the answer to the question. Okay? Example 3 says that George invests $3,000 into an account which pays compound interest of 5.3% per annum, compounded monthly. How long would it take to the necessary month for his investment to double in value? So using the formula, A the amount equals little a times B to the power T over P. He started with $3,000. We want to know how long it would take to the necessary month for the investment to double. So the amount that he ends up with has to be twice what he started with. Starts with 3,000, has to end up with 6,000. And you remember B, as we saw above, is 1 plus I, where I is the interest rate, in this case, per month, because it's compounded monthly. We're given the annual rate of 5.3%, but because it's compounded monthly, we have to calculate the monthly rate, which is what I will represent. So I will be 5.3% as a decimal is 0.053, and that needs to be divided by 12 because it's compounded monthly, 12 times a year. 0.053 divided by 12. So lots of decimals there. That's okay. We're going to keep them in our calculator. but we can write down 0.00442. Right, that's rounded. But remember, b is 1 plus I, so it'll be 1.00442 to the power t over p. In this case, we're trying to find out what t is. How long would it take for the necessary month for the investment to double in value? So remember, p is the growth period. It's being compounded monthly, which would be 12 times a year. So we need to solve for t. Actually, that's not right. I'm sorry. The bottom should be 1. If you look at what we did up top there, in the previous example, it was 48 divided by 6 because the interest was calculated every 6 months. And above here, the denominator was 3 because it was being calculated every 3 months. In this example, it's 1 because it's being calculated every 1 month. So this is going to give us our answer for t in months, because remember, t and p are in the same unit. I would start, though, by dividing both sides by 3,000, which will give us 2 on the left when you divide by 3,000. So 2 will equal 1.00442 to the power t, and we want to solve for t. We can do that by converting from exponential to logarithmic. Start with the base and cycle through. The base of the exponential function will be the same as the base of the log, 1.00442. And again, I've got that number in my calculator. I'm going to use the whole number. So by converting to logarithmic, that's what we'll get. T will equal log base 1.00442, the log of that base of 2. So we want to take the log with, and actually, before I do that, I should add 1 to that decimal, so I have it in my calculator, and now I can take the log. So log with the base set is the previous answer of 2. So there's the answer. We get 157.285. Now, that number, if you round to the nearest month, it'd be only 157. However, you wouldn't have $6,000 in the account after 157 months. It'd be a little less than 6,000. So because of that, we're going to have to round this one up to 158, and then you'd have more than 6,000, but at least there's at least 6,000 there. So 158 months is how long it would take. Okay? So, I mean, here's some more examples of what we've talked about. Using that formula, y equals a times b to the power t over p, where y is the final amount, a is the initial amount, b is the growth factor, t is the time, p is the period time or the growth period. We've talked about it being that. Remember that b, because it's the growth factor, if it's a situation where something is doubling, then b is 2. If something's tripling, then b is 3. If you have a half-life where something's being cut in half, then b is a half. If you have an annual increase of 4%, that's 100% plus 4% more. That's where the 1.04 comes from. An annual decrease of 8%, which means you're maintaining 92% of what you had. So then b would be 0.92. We've talked about the fact that when b is greater than 1, you have growth. Between 0 and 1, that means decay. So just some practice with b, the base, and p, the doubling period. If a certain strain of bacteria doubles every 4 minutes, then b would be 2 because it's doubling, and p would be every 4 minutes. That's the growth period. If you have a half-life of a radioactive substance being 6 years, then b, the base, would be a half, and p, the period, would be 6 years. That is the growth period. And that's how long it takes in order for that substance to be cut in half. An investment triples every 10 years, so b would be 3, and the growth period would be 10 years. If the population of a town is decreasing at a rate of 4% per annum, that means it's maintaining 96% of its population, so b would be 0.96, and the period would be every year, because that's how long it's happening. An antique increases at a rate of 15% per year, so that means it's going to have 100% plus 15% more. B would be 1.15 every year. Right, so sometimes you're going to be given the formula, sometimes you need to come up with it. The number of fish in a lake is decreasing at a rate of 7% each year due to overfishing. You can use that equation. If it's decreasing by 7%, that means it maintains 93%. So B, the base, is 9.93. The 2,500 refers to the initial population. How many fish will there be in 5 years? So that will be when T is 5. So we can just plug that into the calculator to get our answer. 2,500 times 0.93 to the power 5. Whoops. There we go. So approximately 1,739 fish. How long would it take for there to be half the original population? So if they start with 2,500, half of that would be 1,250. And we want to solve for T in this case. First step would then be to divide both sides by the 2,500. So that should give us 0.5 on the left. And now we will convert from logarithm or exponential, to logarithmic. Start with the base and cycle through. The base of the exponential is 0.93, so that'll be the base of the log. Log base 0.93 of 0.5 has to equal T. So we can use our log function. So approximately 9.6 years. In 2002, population of the city was 160,000 and was increasing at an annual rate of 4.5%. So an equation to represent the population of the city as a function of the number of years since 2002 would be y equals A, the initial amount, which is 160,000, times B, which would be 1.045. It's increasing at 4.5%. So you're going to have 100% plus 4.5% more. To the power T over P, which would be 1. P would be 1 because it's increasing every 1 year. So, I mean, that's just going to be T. The population in 05, that's 3 years from 02, so T would be 3. One 586.58, so approximately 182,587. If the population continues to grow at this rate, determine the number of years it would take for the population to double. So if they start with 160,000 to double, there'd be 320,000 people in the city. And we want to solve for T. Dividing both sides by the 160,000 will give us 2 on the left. And then to solve for T, we can't make the bases the same, so back to converting from exponential to logarithmic. Start with the base and cycle through. The bases are the same no matter which form you're in. So T will be log base 1.045 of 2. Approximately 15.7 years. A certain bacteria strain doubles every 6 hours. If the number of original bacteria was 350, how many would be present after 28 hours? So using our formula, y equals a times b to the power t over p. In this case, we're not given an initial amount, so we can pick, oh, I'm sorry, we are 350. Initially, there were 350. It doubles every 6 hours, so our base will be 2. That's our growth factor. How many bacteria will be present after 28 hours? So that's our time, and our doubling period is every 6 hours. So we can punch that into our calculator. So approximately 88, 89.4 bacteria. Yep. Next one says a patient who was feeling ill had a sample of bacteria taken from her throat. Sample contained 354 cells. 24 hours later, the sample was recounted and was found to contain 8186 cells. Determine the doubling period of the bacteria to the nearest tenth of an hour. So Y is the final amount, which was 8186. A is the initial amount, which is 354. B is our growth factor. We're asked to find the doubling period, which means that the growth factor is 2. The number of bacteria is doubling every so often, and that's what we're trying to find. What is the doubling period? If the time that had passed was 24 hours, what is the doubling period? So I would divide both sides by 354 as an initial step. So 8186 divided by 354 is that decimal 23.124. That's what 2 to the power 24 over p will equal. And I will now convert from from exponential to logarithmic. It'll be log base 2 of 23.124 equals 24 over p. So before I grab the calculator, let's get p by itself. You can multiply both sides by p first. And then divide both sides by the log to get p by itself. And to the nearest tenth of an hour, we'll get our doubling period by going 24 divided by log base 2 of the previous answer. Use the entire decimal. So 5.3 hours. Let's see if it makes a difference if we don't use the entire decimal. How much of a difference it makes, if any. It'll be log base 2, 24 divided by log base 2 of just 23.124. So you actually would get the same answer if you rounded to the nearest tenth in that case. But you've seen that's not always true. A radioactive isotope has a half-life of approximately 30 minutes. How long would it take for 320 milligrams to decay down to 10 milligrams? So our formula is y equals a times b to the power t over p. The amount at the end is going to be 10. They start with 320. We're told there's a half-life, so the growth factor has to be a half. And the half-life is 30 minutes. That's our p. We need to find out what t is. How long would it take for that to happen? Divide both sides by 320. So 10 divided by 320. 0.03125 will equal 1/2 to the power t on 30. And now we'll convert from exponential to logarithmic. It'll be log base 1/2 of 0.03125 equals t over 30. And then I'd multiply both sides by 30 before I even grab the calculator to get the t by itself. So 30 times the log with a base of 0.5 of that previous answer, 150 minutes. The fact that we actually get a number like 150, which 30, that's the half-life, divides into evenly, tells me this one could have been done just by using the calculator and some logic. If you start with 320 milligrams, well, after 30 minutes, there'll be half left, so divide by 2. So after 30 minutes, there's 160. Divide by 2 again, that's the amount after 60 minutes. Divide by 2 again, that's the amount after 90 minutes. Divide by 2 again, that's the amount after 120 minutes. Divide by 2 again, that's the amount after 150 minutes. Okay? So this one could be checked just by using some simple logic. Example 6, population of germs on a dirty countertop doubles every 25 minutes. How long to the nearest minute would it take for the population to triple? So this is one where we're not given the initial amount. So we can just make an initial amount up. If we start with 10, then if it's going to triple, there'd be 30. I'm sorry, double. Doubles every 25 minutes. How long would it take for the population to triple? But the fact that it doubles every 25 minutes tells us that we are going to have a base of 2. And the doubling period is 25 minutes. So when I use this formula, again, as I said, I'm going to make up an initial number. So if I said that I started with 10 bacteria, we want to know how long it'll take to triple. So that means we'd have to end up with 30 bacteria. But it's doubling every 25 minutes, so our base is 2. And our doubling period, our growth period is 25 minutes. We want to find out what T is. How long would it take for the population to triple? If you divide both sides by 10, 30 divided by 10 is 3. And that'll equal 2 to the power T over 25. And now we'll convert to a log. Start with the base, cycle through. We'll have log base 2 of 3 equals T over 25. And then if you multiply both sides by 25, we'll get the log by itself. (25) times the log base 2 of 3. So approximately, it says to the nearest minute, so approximately 40 minutes to the nearest minute. Number 7, in April of '86, a nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine-131. The half-life of this was 8.1 days. Determine the number of days to the nearest day it took for the level to reduce to 25% of its original level. So the amount at the end y would be 25% or 0.25 of what we started with, which is A. A is the amount that we start with. Because we have a scenario where the amount of this is being cut in half, we have a half-life of 8.1 days, so that is our base, a half. We want to find out what the time is it took for that to happen. So basically you'll have 1/4 of what you started with. Now you can divide both sides by a little a and they'll cancel out. So that leaves us with just 0.25 equals 1/2 to the power t over 8.1. And this one we can actually solve without using logarithms, because 0.25 is the same thing as 1/4. And 1/4 can be written as 1/2 all squared. Whoops. In this case, we were able to make the bases the same, so the exponents would have to equal each other as well. So 2 will equal t over 8.1. Multiply both sides by 8.1, and you're going to get 16.2. To the nearest day, approximately 16 days. Now, it's true, you could argue and say, well, no, because at 16 days, it'll be less than 25% of the original level, so therefore you'd have to round it up to 17 days, and that's fine. Okay, that's fine. All right. So there is an assignment there that you can work on. I will post the answers to Google Classroom so you can check your answers. Remember, tomorrow we have a quiz. And there's actually a couple assignments here, I think. Yeah. So there's 3 pages of questions. I will post the solutions to all of them to Google Classroom. Remember, tomorrow you're going to have a quiz on Chapter 8. And then our exam will be on Thursday. Okay. So Wednesday we'll go through the quizzes for Chapter 7 and 8 that you've written. If anyone didn't get the unit review, well, I think most of you did because I only got 3 sitting here, so, but it's up there in case you didn't. Okay.